All right, this is going to be a review of problem 3B.2, review and answering the problem basically. So the first question is verify that the velocity distribution for the laminar flow of an Newtonian fluid in a duct of this type is given by that equation. So basically for this type of duct. So basically what we're going to do is we're going to use the equation of continuity, equations of motion, and we're going to solve that equation. We're not going to get any boundary conditions at all. We're going to take this. So when you do the equation of continuity and the equation of motion, there's going to be like double derivatives, dvz dx and dvz dy, because there's these x and y direction walls. And so we're going to take the derivative with respect to double derivative with respect to x and y in this equation, and then we're going to insert those derivatives into the equation of motion that has those double derivatives in them. And then if these inserted double derivatives from this equation into the equation of motion lead to like a valid equation that's true. So basically it doesn't say like 5 equals 4 basically. So the equation is valid for all the conditions, all the coordinate conditions that land within this triangle, then we can say the equation is true. So yeah, let's get into it. All right, so we're going to use Cartesian coordinates, equation of continuity, B.4-1, equation of continuity, Cartesian coordinates. So that's this equation, and that's going to be, right here. So eliminate this because it's steady state, eliminate Vx because there's no velocity in the x direction, eliminate Vy because there's no velocity in the y direction, and you get ddz rho vz equals 0. So therefore this expression equals 0, and dvz dz does not, or vz basically doesn't depend on z basically, so that's what you get from that equation. And then the second equation we use is the equation of motion, B.5. And we're not using these equations because they're more complicated and you have to get the definitions for each of these normal and shear stresses. Basically, it's kind of annoying to do that. So we're using them with constant density and viscosity, and that's because we're in a chapter that assumes Newtonian fluid, so we can use these equations, and where the definitions for the shear and normal stresses are basically given. And so we use B.6-3, and that's because you see this GZ, the velocity is the GZ, so that's basically how you know that which of these three that you're going to use. Basically, the velocity of interest is the one that you use. So if there was a Vx, Vy, you would also have to use these equations. But since it's just Z, you only have to use this equation. All right, so yeah, that's that equation there. It's B.6-3 actually. Yeah, B.6-3. I must have done a mistype there. So dvz dt equals 0 because it's steady state. Vx equals 0 because there's no Vx velocity. Vy equals 0 because there's no y velocity. Dvz dt or dvz dz equals 0 because of the equation of continuity. I explained that earlier in this last equation. Leave dvz dx because it does depend on the x. Leave this because it does depend on the y, and take this out because d squared vz dz is again 0 because of the equation of continuity. All right, so write out the simplified equation. So dp dz equals the final value minus the initial value over the final position minus the initial position, and you can only do this when the relationship is completely linear, like over the range. So like if you had like x squared, you wouldn't just be able to put the final initial values or the final initial values for the derivative of x squared. Yeah, that makes sense because x squared is not linear. So, but this relationship is linear, and we know that just because we know how pressure works, basically. And so here's a definition for um, partial pressure or pressure at zero point 0 PL and PL, basically this expression basically. And this is explained more in depth in 3B.3, but I won't explain it again here basically. But yeah. Okay, so now we conglomerate these terms into this and transform. Now we transform the equation of continuity with definition. What does that mean? Okay, yeah, so yeah, we're just plugging this in for these two terms basically up here. So transform. We were using fancy words for some reason. All right, so now boundary conditions at the law of the wall. I don't know why I really wrote this here because you don't really need it, but we're going to expand the given velocity profile to get d dvz squared dz squared and dvz squared dx squared, or dvz squared dx squared and dvz squared dy squared, and then we're going to plug those in here and we're going to see that this equation is true basically. So yeah, so this equation is from the answer that it gives us. Oops. Yes, it's just this equation. So we're just going to expand it out to just make it easier to do the derivatives. Yeah. See how we get this? And so dvz dx. So you just take partial derivatives. So this is, you just treat the y. If you're taking the derivative with respect to x, you just treat the y's as constant, and you treat the x's and all the other variables as constant, basically. So yeah, it's just going to be 3x or 6xy minus 6xh, and yeah, adding all these extra terms. And then you take the second derivative, you get 6y minus 6h, yeah. And then you just do the same for y. Um, that's pretty easy to understand. Just do the same thing again. So now we're going to plug in these definitions, each of these definitions, into um, this equation and verify that it's true for all the boundary conditions. So yeah, I guess that's why I wrote those boundary conditions here at this point. Probably should have written them later, but yeah. So yeah, just insert those equations with the conglomerates. So yeah, they both have the same conglomerate, so you could just put them all together, factor out the viscosity, cancel out the 4 in the numerator denominator. Okay, yeah, so these cancel. Which becomes 4. This becomes -4. This becomes, yeah, okay, so cancel out the 4, cancel out the h in the denominator, cancel out the viscosity, and you get 0 equals this expression basically. And yeah, that's just true. Like, it's like 1 equals 1. So that's true for all coordinates. So there's not really much work there to verify that that's true because it's just obviously true. All right, so now for part B, we are finding the velocity profile and the mass flow rate profile, which is pretty simple. Well, the mass flow rate, not the mass flow rate profile. It's the same for the whole thing. Um, yeah, so let's do that. So yeah, the average velocity is the integration of the velocity profile Vz of the axis perpendicular to the flow direction dA divided by that perpendicular area. So basically, um, the integral over dA of Vz is like all of the velocities over the whole area, like it's like the area under the curve. So basically, and then you divide by that area to get the average velocity. It's kind of, I don't know. If you get it, you get it, and if you don't, um, you will eventually. Basically, I don't know. It's hard. It's kind of hard to explain a little bit, but you can. It can also be modeled as the integration of dA with no equation. So it's just another way to get the area if you don't exactly know, or it's mostly a way to verify your dA because you can find A pretty easily, just the area of this triangle. I mean, that's kind of like the easy part, but it's a good way to verify that your dA is the correct one, basically. So yeah, so this is the differential area that we're trying to model for. So it's like this little split, and it moves up and down based on. So dx dy is right. So from y to the over root 3 to negative y over root 3. So that's just from, where did I put the shape at? I miss it. It's right there. So yeah, from this end to this end, I'm just solving for x in these two expressions, and I get those negative expressions on each end of the bound, and I go y equals h to 0. So it's self-explanatory, but I guess my original approach is just wrong. I feel like I remember this now. Yeah, but yeah, so I finally got the answer with the integration. Really annoying. So now to find the max velocity, use dvz dx and dvz dy, and set those equal to 0. And when they're equal to 0, they're either equal to max or min. So basically, when they equal 0 and they're not on the wall, that's how you know it's a max. So we're solving dvz dx equals that, dvz dy equals that. Assume x equals 0, then why are we assuming x equals 0? Oh yeah, because we're assuming that the max velocity is going to be somewhere on this axis, and that's because it's farthest from either of these two walls. So we're just assuming that. It's kind of a that's like it makes sense that you would make that assumption. But so yeah, that's why I make that assumption. Then 2y h equals, so yeah, so we're just solving, saying x equals 0 here, and we're solving for y. Yeah, we're just getting rid of this expression here, because you could just divide that out and it's 0. So it's going to be 0 equals 3, or it's going to be 3y squared equals 2yh. And yeah, so that's what I get. So divide by y, you get 2h equals 3y. And then you divide by 3 and you get 2h over 3 equals y. Yeah, that's what you get. And then also, if you plug in 0 for both of these, you also get 0, 0 for that point. And yeah, it's not gonna be this point, and that's because that's a velocity equals 0 boundary point. So that's a minimum velocity. So when you're taking a derivative, you're either going to find maximums or minimums. So at 0, 0, that's a minimum because it's at the wall, so you know that's a minimum. So then we basically, just from that, we know that the other point is the one that's correct. And yeah, so we plug those points in. Oh yeah, so yeah, this was the answer for the average velocity. I don't know if I actually explicitly said that, but so yeah, you plug this in to the velocity equation, and then you get Vmax. Vmax what? I don't know. That's kind of weird. Like I said, it's definitely this equation. I don't know what I was doing with all that other shit, but yeah, this is definitely VZ max. And divide this by this, you'll get 27 over 60 because it's 1 over 27 divided by 1 over 60, and that's 27 over 60. 27 over 60 simplifies to 9 over 20, which I think is the answer for the problem of that. Yeah, 9 over 20 Vmax, so that makes sense. And now we're just doing the mass flow rate, which you multiply by the area, and multiply by rho, basically. So area equals h squared divided by root 3, and you can look at the formula. You basically just do that. H equals h squared divided by root 3. Oh, I guess that's from the integrating earlier. I guess somehow the A was right, but my integration was wrong, I guess. I don't know. I probably just made an integration mistake and it just wasn't working out originally. This is the differential area that we're trying to model for. So it's like this little split and it moves up and down based on coordinate y. So the height of dA is y plus delta y. Or so yeah, dA is just this little slit and it's moved up and down the shape when the y coordinate changes. So the height of this dA is just the height of this little slit, and that's y plus delta y minus y, or you could just say it's delta y. It's just this thickness of this slit, basically. So yeah, I don't know. It's pretty self-explanatory. And the width of the bottom height is y equals 3x, and that's just because this end of the triangle, or this side of the triangle extends y equals 3x, and that's only half the width. So yeah, so that's at the lower portion. That's it, like here. So yeah, so y equals 3x, and then x equals y divided by root 3. So you just solve for x and dA, and then you double the width because obviously it extends in both directions. And then you also have to find the higher width, because to find the area of a trapezoid, you have to take the average of the two widths and then multiply by the height, basically. So yeah, the width of the top height is y plus delta y equals 3x times 2, basically. Solve for x, you get this, and then you got to multiply by 2 for the same reason, which is just because it extends in both directions. Pretty simple. So yeah, x equals that, and then you just take the average of those two widths, and you get 2y over root 3, 2y plus delta y over root 3, basically. 2y. Does that make sense? Yeah, I don't know. I'll believe it. So yeah, now you just multiply those. You multiply the height of the thing by the width, the average width of the thing. So the height is delta y, and the width is the average width is 2y over root 3 plus delta y over root 3. Oh yeah, so that makes sense. Yeah, so that makes sense why it's just there's one delta y. But so yeah, you're multiplying those two together. Yeah, same as dy. Delta y is the same as dy. That makes sense. And you eliminate this term because the delta or the dy in like an integral is like an infinitely small term. So the root of like an infinitely small term, like -1 to the -9, is the -1 to the -18, and that term is like infinitely smaller than an infinitely small term already. So basically, you just eliminate it. Yeah. So this is from the integration. The integration of dA equals a. So yeah, that's how we got that. So yeah, this mass flow rate equals density times average velocity times area, and mass flow rate equals this, which is the answer.